Good morning, good afternoon, everyone. Welcome to our joint seminar series of water economics and politics, which is joined between University of Cape Town in South Africa and UC Riverside in United States. Today, we are delighted to have Professor Medellín-Azuara. Josué is a professor of civil and environmental engineering at UC Merced. He also serves as an associate director for the UC Davis Center for Watershed Sciences and UC Agricultural Issues Center, and as an adjunct research fellow at Water Policy Center of the Public Policy Institute of California, which is known as PPIC in California. At UC Merced, he's one of the inaugural agronomist faculty of its Agriculture Experimental Station. His expertise includes water resources management for agriculture, communities, and the environment. He's a principal investigator for studies on drought, climate adaptation, consumptive water use, and policy analysis for regulations with emphasis on California, state and federal agencies, and national science foundations. He also has been an advisory committee on climate managed aquifer research, Delta Drought Response Pilot Program, Delta Science Advisory Board, and Delta Science Task Force in California. Currently, he serves as a member of National Academy of Sciences, Engineering and Medicine Ad Hoc Committee for the review of the long-term operations of the Central Valley Project and the State Water Project. Professor Medellín-Azuara holds degrees in engineering, business, and economics, and obtained his PhD from UC Davis with his dissertation on managing environmental flows in the Colorado River Delta. We are very happy to have you. Thank you for joining us, Jose, especially given that you are on your family time. We appreciate it. The floor is yours. We have about 30 to 40 minutes for presentation, and then we will have a Q&A. Please, if anyone has a Q&A, submit it through the chat box, and then at the end we can, you can just open your mic and ask your question if you like to. If not, I can read the question. The floor is yours, Jose.
Thank you very much, Mehdi, for the nice introduction. Don't worry about my family. At this time, they are done with me for the vacation. So we're going back to California just tomorrow. So thanks. This is seems like it's a great seminar series, and as the name says, we'll present what we've been doing on climate extremes in agriculture for California using hydroeconomic models. So this slide comes from a book of Elena Cariol Dinar and a few others, and it never gets old to me. For those of you not familiar with California's climate, the blue in the left means areas with the highest runoff, the red, the areas that contribute very little runoff. And for that, we have a highly engineered water supply system that runs north to south, east to west, with a vast infrastructure, one of the most engineered in the world. And that has allowed the establishment of an agricultural powerhouse and large cities that are driven by many economic sectors beyond agriculture now, with more concentration on the services industry. This is a map of agriculture in the United States. You can find the reference there. You might have seen this, but you can see that in the California state, it was a little bit of cattle, citrus, some rice here and there, and a few other crops. So there was this was in a time in which agriculture was not as diversified. But the agriculture footprint today has changed dramatically. So now we have 3.8 million irrigated hectares, 9.7 million hectares on farms, more than 300 commodities. This map is from the crop CDL, from the NAS CDL layer, and shows you a very colorful mosaic of crops all over the state. it supports about 450,000 jobs, more like 420. You will see some stats there, 55 billion in gross revenues. From those, 25% are in animal products. And that motivates a lot of the study we're conducting on climate change that is looking into the animal operations as well, because they rely on crops grown in California, and they use a substantial amount of water along with the other crop mix. So this map is Kern County. Is an animation, is just a GIF. It's kind of old now, but it's Kern County. It's one of the either one or two, depending on how on what Fresno produces and the year type and a few other factors. But shows you how early in the 1990s there was more annual crops than perennial crops. So there's a substantial growth in perennial crops, and that has come to a sustainable level. So that is one of the things we want to address with policy and managing water with resources. So this shows you a similar graph with trends from 1980 to 2020. We only put there like 4 crop categories, just because it would be very overwhelming and useless to see the 300 commodities. But if we group into trees and vines, field and grain, vegetables, alfalfa, and pasture, you can see there's definitely a growth in trees and vines, and there's a substantial decline, some on field and grain, and in alfalfa and pasture are kind of declining a little bit, but not too much, because they have to support a lot of the beef cattle and also the dairy cattle. The alfalfa can be imported from other regions. The main hub for dairies, for example, is in the San Joaquin Valley. Used to be in Southern California, a big hub, but the dairies have moved. But the alfalfa can be imported. The corn silage cannot be. So that puts tremendous pressure on crops. The map on the right shows you the kind of crops that we have right now among these categories. You can see that the Central Coast, the coastal areas are largely high-value commodities, vegetables, non-tree fruits, many of the commodities that grow in that kind of weather, and that can make the business case for such an expensive or costly water in the coastal areas. And then you get the North Coast, which is also a coastal area, obviously, with some pasture for cows, and also some vines and a few other higher value commodities. So let's see. The permanent crop coverage has been increasing in the Central Valley. This is a map from Spencer Cole, one of my former students, in a recent publication, a policy brief. You can see here the areas that are priority basins in brown, and then you see critically other bracketed basins in purple, and other non-sigma areas, such as the Imperial Valley, where a lot of the Colorado River water is used. So you can see here that there's a decline in a lot of crops in California, particularly the annual crops, which are in the medium gray bar, but in much less reduction in an increase, in perennials. So you can still see that decrease in perennials with net reductions in irrigated areas, but still a little bit of growth on perennial permanent crops that can cause some water inflexibilities. These are some statistics from the California Department of Water Resources, mostly on the portfolio of water sources. We have a highly diversified portfolio of sources. We have diversions out of the water rights system. We have imports of water that come from those two large projects, the State Water Project, the Central Valley Project, that provide water for agriculture and cities, and have these two arteries on the Central Valley that use pump from the Sacramento River Delta that serves as the hub of the water system. And then you can see here there's some the use is on the left, the supply is on the right. This is for statewide. It shows you a year in which there were more or less abundance of water resources. 2019, kind of a normal or even a little above average year, and then 2021, a year in which we had a drought, and then there were reductions in, as you can see, environmental uses. So you could see the irrigated agriculture uses more water, and we will discuss of that a little bit according to the WR, and also quite a reduction there on wild and scenic rivers, which is what usually takes the heat on dry years. Then you have a little bit there of stream flow. These are percentages though, so these are not absolute numbers. Then you get the supply sources, and you can see in a normal year, you get this like 2019, to call it normal. There's no normal anymore. Anyways, you have a lot of groundwater use, so a substantial increase in the droughts to in groundwater pumping just to satisfy the demands from all crops in the state, particularly to Latter Lake Basin. The map on the right, it might be familiar for you. It's just shows you how much of the total water supplies is supplied by groundwater in each of the 10 hydrologic regions. You can see that at Tulare Lake Basin, nearly half of nearly a third or something like that. No, nearly half, sorry, of the supply there. A little bit less on the San Joaquin River Basin, and definitely a third or so in the Sacramento River Basin. You can also see the Francisco Bay. Well, they have aqueducts that come through the from the Sierra Nevada mountains, and you can also see North Coast, largely surface water supply, Central Coast groundwater, Southern California, a lot of imports, and Colorado River region, definitely surface water from the Colorado River, and we will talk some more about that. This is one of the most useless charts produced by my colleagues, with my apologies for them, the Department of Water Resources. There's nothing you can see there. And the point is called the California Waterfly, and it shows you water use and water supply. And they now have it interactive. I downloaded this for the state, just to the presentation. What in essence shows you that agriculture is really very stable in terms of water use, regardless of the year type. There's a little bit of following, but most likely stable. Is the environmental uses, the wild and scenic river and stream flows that take the heat on the reductions in water use on all this historical time. And then you can see on the right the water supply for the water supply. What are the in-stream environments? Recycled water, very little recycling in the state, and pretty fixed on the Colorado River due to our seniority in water rights, but that is kind of about to change, as some of you heard. So this shows you, what varies the most essentially in the water source, and you can see groundwater comes to play, and a few others. By large, the atmospheric rivers provide the most variability in the surface water that we have to use for crops, environment, and communities. So we have these currents of moisture, no new to many in California, that just hit the Sierra Nevada, and the difference between a wet year or a dry year is just this ridge, this low high pressure zone that is on the that gets in front of the California coast and just deters or, if not existing, just allows these currents, these atmospheric rivers, to heat our water system and get water. So 2-3 atmospheric rivers can make a big difference. We had a parade of atmospheric rivers in 2023, more than 30, close to 40, if I'm not mistaken, atmospheric rivers, and that resulted in the reappearance of the Tulare Lake, if you remember, in the winter of 2023. So this varies a lot, but there are years in which we don't have that variability. This is an old graph at this point from a PPIC report that we put together, and shows you that precipitation, goes this volatility. You have very little in terms of what is a normal year, which it will be like no bar in that year, and you have a lot of extremes. So this is all. But one thing that you can notice on the bottom chart is that there's a trend in temperature, and this increase in temperature, and that obviously has some implications for water supply, particularly for crops. So this is a cartoon I stole from one of my colleagues, but slice and is from the Sacramento Bee, actually, and shows you how the state looks into after a couple of years of drought. The reserves in 2022 were very, very low for the major reservoirs, and that started creating some problems. So if it was not for Miracle 2023 that I showed in the previous slide, the picture would have been very different for agriculture. So I'm moving now to some drivers of change, or you can see on the left chart that I put together for a paper with Jay on what is the value in the gross revenues and the employment. And it's at this point a little bit old. I'm about to update the chart. Shows you if we have 9.3 million acres of crops and just line them up from the least valuable to the most valuable, you can see that about 85% of the revenues, or the gross revenues, the value of crops, and also the employment is in fruits, nuts, and vegetables. So these hold the most value, have a lot of the employment. And then in droughts, what you can see, and when I put a pointer here, is that you usually start following from right to left, right? So you start following with the field crops, grain crops. Rice is a big donor, to call it somehow, of water during droughts. And a few other crops as well. But these crops here support the dairy sector, so there are some flexibilities in particularly in corn silage that has to be grown in very close to the dairies, and we will talk about a little bit in a few minutes. So this is the value of water. This is from a more recent publication from PPIC, from Peterson et al., and shows you there's an intensification of value. So we have a higher value per unit of water use, higher value for per unit of land use. So we can see this trend. And at the same time, the percent of the percent of the farm GDP as a percent of total is going down, as you can see in the chart. So here shows you another driver of change of the agricultural landscape, and is no new to anyone in California. Environmental flows. There's a regulation looking into increase the outflows in the delta for water quality control, both in the lower San Joaquin River and also in the Sacramento River Basin and the delta. So those are sizable cutbacks of water that the state is looking to reduce diversions. and that will mostly affect irrigation districts in the San Joaquin River and some areas also in the Sacramento Valley. So that environmental flow again is a big driver of will be a big driver. But by far the largest, the climate change, obviously, there will be an effect on the supplies, and we will deepen into that anymore. But by large, the largest effect on water supply, or the largest shortage, will come from groundwater limitations due to the Sustainable Groundwater Management Act. And you can also see here in the middle graph, it shows you dry wells due to overpumping. And that has an effect on communities, mostly that they rely on shallow wells. And therefore, there's a lot of interest in the groundwater sustainability plans and as part of SIGMA to protect these shallow wells. So we use hydroeconomic models for predicting cropping patterns. So this shows you a little chart here. We usually use a C2B SIM as our source for groundwater availability. We use an agricultural production model called OpenAg. You can take a look. It shows you a little bit of an animation there, if it works. It does never work, but shows you some of the settings that we can put in the model, and that you can just see what are the differences in revenues, cropping patterns, jobs, GDP, and a few other indicators for these for the entire state. We're doing this as part of the drought assessment for the California Department of Food and Ag, and also as part of our climate change assessment on agriculture. So with this, we can see changes in revenue. So we use a calibration year, let's say a year with plenty of supplies, such as 2020, 2019, and then we start cutting back water and just have a model, it's a deterministic model to optimize based on maximization of profits, calibrated to kind of a baseline observed values. And with that, we estimate changes with respect to baseline conditions and in the corresponding impacts. This is a project that I co-lead with my colleague, with Alvarez Cribabao at UC Davis and a few other researchers. Again, this is take a look. There's the website. We can give you access to it if needed. So this shows you some impacts that we did with such model on the 2022 drought. And the reason I bring this is just because every drought is different. And the drought of 2020, 2022 was a drought of the Sacramento River Basin. So the area that is more water abundant at that time faced severe shortages and had the largest amount of fallowing. A lot of that fallowing was from rice, because rice is a little bit more flexible, same as alfalfa in a way, and a few other field crops in not irrigated or fallowing land, given the lower net returns or the lower returns from cultivating some of these field and grain crops. So we estimated 750,000 acres is at that time. It's more like 700,000, but still substantial. There were some job losses in 12,000 out of 420,000 in crops. So the number might seem little, but these belong to the lower income groups in our state. So we definitely need the state provides some sort of emergency services or some assistance through emergency services to for support some of these populations that are affected. Also dry wells. Some dry wells occur in and therefore the state comes and supplies some communities with water to face those losses. So the 2023 year was all the contrary. As I was saying, it just came as one of the wettest years. You had the reappearance of the Tulare Lake. This we use a Sentinel image and in Kishore, Siddharth Kishore, one of the postdocs in my group, formerly with Mehdi, Nemati, and the UC Riverside group, is leading this study on flood. We're looking into the aggregating these losses. Were about, we estimate about 80,000 acres of losses, with 170 million or so of revenue losses compared to normal water years. So in terms of climate change, what we've been doing, this is preliminary work again, is looking into impacts on the Central Valley, the Colorado River region, and in the coastal areas. This is from an estimate using the calcium tree model. The calcium tree model is the one employed by the California Department of Water Resources and the Bureau of Reclamation to simulate operations of the Central Valley Project and the State Water Project. The coverage is not statewide, so we need to employ other models to simulate areas not covered by calcium, but by large covers a lot of agriculture in the Central Valley. In here, you can see on the graph on the left that depending on the year type, whether it's normal, again, there's no normal anymore. Historical conditions are on top. So you can see there the orange, and then you can see on the bottom some climate change. Then you have climate change and allow some trading, and then climate change, and you get like more water for communities or for environmental uses. And then you have climate change plus a flat reduction, which is one of the largest scenarios. These scenarios are being changed. This is from December. My colleague Alvarez Cribabao presented this in AGU. And one thing you can notice is that between historical and climate change, the losses, the revenue losses anyways, are not as impactful as one might think. They are in the hundreds of millions of dollars, not in the billions, definitely. But the problem is that when you compound other effects, such as the increased evaporative demand in crops, or groundwater regulation, or the environmental regulation for sigma, these impacts magnify, and this is what we're trying to examine here. So I have to be careful because a lot of my colleagues here in the call are more of experts on the Colorado River than we are. But what we've been, in my understanding, the long-term cutback on the Colorado River, regardless of climate, is looking just shy of 500,000 acre-foot of cutback for California, mostly observed by agriculture. I think it's 80 to 90%, depending on the conditions. There's some guidelines on the right that are current on depending on lake mid levels, but in most cases, California gets its water allocation of 4.4 million acre-foot per year. With right now, some reductions have been happening as part of the tri-state agreement, California, Arizona, Nevada, and with some commitment with for the Bureau of Reclamation. So the cost of that, based on the current value of agriculture in this region, could come close to 800 to 2.1 billion. So this is some of the quantifications we have been working with. Next slide, sorry. So what coastal impacts, and I'm just bringing back the recent drought map from the previous slide. It shows you that agriculture losses in the coastal area suffer mostly from water stress and wildfires. So the northern part of the state, some of you know, the north coast had some wildfires on the 2022 that damaged some of the grapes that are used for wine, and that had a severe impact on the industry. It was important locally, not as statewide. It was not as much. Coastal areas also on the Salinas Valley, the central coast, they can be affected by groundwater nitrate regulation, but it's mostly stable so far. So they don't get as much losses. In last time, most of the losses occurred in the north coast, Mendocino, Sonoma, and other areas. The urbanized areas in Ventura, Southern California, are more likely to be ceding to urbanization pressures in the state. And well, we just discussed the Colorado River for Imperial and Palo Verde and Coachella irrigation districts. So, so this shows some work of Dr. Siddharth Kishore. So it's preliminary on the effects of temperature on crops and milk yields. There has not been a comprehensive update on the potential impacts of yields, to our knowledge, anyways, on crops in California. We have employed the 20 crop groups categories by the Department of Water Resources, and we want to see what is the effects of extreme crop, the extreme temperature on the crop yields and irrigated acres. So we find that has a negative impact on yields of citrus and subtropical trees and vineyards. And the extreme temperature is associated also with a decline in harvested areas for some crops, such as flour, processing tomatoes, and onion and garlic. We also look into the milk production. What is the effects of heat stress on delicate milk production? And we find this U-shaped relationship between heat stress and milk production. So there's a point in which the heat helps, but after that it reduces the yield. So there are some non-linearities here. We used USDA, NASA Agricultural Statistics Service, 1980 to 2022. Siddharth obtained climate data from GridMet, 1979 to 2020, and there took some regressions here. We have this for all 20 crop categories in the Department of Water Resources. So this shows you the various temperature beams, and then we look into the logarithm, the natural log of the yield, to see how much is the approximate change. You can see with some exceptions, there are some crops that see some reductions depending on the time of the temperature beam. I would say these are not as catastrophic or as except for a few crops. This shows you the same effect on harvested areas. Again, the effect goes mostly for controlling for variables for weather, controlling for county and year fixed effects. We can see that tomatoes might see some reductions, the processing tomatoes, and a few the fresh tomatoes, and you might see the similar behavior for a few other crops, but still the effects seem relatively minor. This shows you that increased temperatures have a positive effect on rice and cotton crops. So This is consistent with some literature finding that some of these crops are more sensitive to climate. So yeah, and this is again, I think this is the same chart. Sorry. These are some. Now we also examine the effects of temperature, humidity, adjusted on dairy cows, so to see how cows, by response to this temperature, humidity, stress or index, and use milk yield obtained from the USDA and also county level cow inventories and climate data obtained from GridMed. We see some interesting trends here. You can see here there's a natural, like a seasonal productivity in milk yields that you can see that the spring months we have some more productivity that starts declining. You can see also the milk yield per cow per day has along this time has increased. So improvements in technology. So it's probably a ration and management. So maybe some factors that have motivated this increase, because you can see the scales are a little different between charts. But you can see over different historical periods what is this response to stress on milk. You can, and what we find is during summer, an absolute decline of 3.5 kilograms per cow per day in milk production is what we could expect under future climate conditions. Another effect that we might that you've probably seen also in the literature is the higher evaporative demand in crops. This, of course, varies depending on the crop type and the atmospheric carbon concentration and many factors. But overall, we can see here the water year evaporative demands. This was put together by my colleague, Josué at UC Merced, a climatologist, and shows you the water year precipitation in inches, and also shows you the evaporative demand. And you can see that in the latest drought, this is 2022, and I want to say this is 2021. These are the two highest consecutive years with the higher evaporative, or with the highest evaporative demands. So this it might sound like a very little. We have also a paper by Moyers and others, including myself and Josué, that shows you higher evaporative demands of around 4.5%, which 2-4 more inches of water might not seem like a lot, but when you multiply that by the area of the Central Valley, let's say 6 million acres, then that is roughly the size of a reservoir, just like Folsom, that is 1 million acre-foot of water, just because of this increased demand from higher evapotranspiration. So Sigma has been in rethinking a lot of this. You see in publications that 550 to 900,000 acres had to be reduced depending on what we do about trading, recharge, and a few other things. This shows you reduction. This is from my colleague Alvarez Cribabao, and talks about reductions. You've seen this in another slide with considering environmental flows on the Sacramento, in this case, it's the San Joaquin River, lower San Joaquin River, climate change, and Sigma. But you can see that by far the largest reductions in water available come from Sustainable Groundwater Management Act. So that can, in a way, blur a little bit what happens with water supply for agriculture. Then on the San Joaquin River, too, same publication, same work from a couple of years ago, we see that depending on the trading and also expansions in supply, mostly due to recharge, we can substantially reduce The amount of water is roughly the same, unless water cutback, unless we do some banking with groundwater banking, groundwater recharge. But the land following can be substantially reduced if we expand trading either locally, regionally, or valley-wide. And that can also substantially reduce the agricultural losses and the job losses. So communities suffer from dry wells and also in a way from this idling of land that is expected. So there is some hotspots for water supply that are not covered, and then they have to the state intervenes, sometimes providing some support through emergency services for paying bills and also supply water, drinking water when we get into dry wells. Despite that, this following land, the employment in the regional employment has been very, very stable on statewide. This shows you crop production, food manufacturing, and contract labor, which is the lower yellow line, and shows you that the years of the drought, there was like a slight decline, but we're facing actually shortages of labor in agriculture. So this is unlikely to be affected too much from what we've seen. On the contrary, there's a shortage of labor, and it's been a challenge. So this shows you for food and beverage manufacturing. So this shows you with information from EDD. There's an expansion in the beverages sector, as you can see, and also other food manufacturing. So you can see that employment is more or less stable during, regardless of drought. That said, there will be inevitable permanent land following in the order of 550, 900,000 acres. Solar is looking very promising, but and well, there's a little bit on forages that can be grown with without too much irrigation, and there's also opportunities for habitat to come in. Obviously, in all these projects is how are these gonna be paid statewide, right? And in recharge base, obviously is the main source of overcoming the overdraft. So looking forward, I put a very nice picture here generated by ChatGPT that shows you the agriculture in the future. And not sure it's the most precise picture, but shows you that we're also very adaptive, and agriculture continues to be the largest water users. The climate volatility and regulation might force this creativity in planning, and universities are definitely important partners on this. So looking also into alternatives like managed aquifer recharge, land repurposing, trading, automation might help reduce the impact of regulation in climate. So climate extremes will likely affect in a negative way. There are potential yield-related declines. We see some signal for some crops, and also a little bit of decline also in the production of milking cows due to induced stress. But overall, they do not seem catastrophic in my the technological improvements might catch up with some of that in the long run. Yet they are there and are significantly statistics following the research from Dr. Kishore now on the works. Impacts can be compounded when we put it in groundwater regulation, environmental protection, and also the increased evaporative demands that will filter this gap in the available water and in the needs of the crops. And then water trading, flexible allocation schemes can be useful for mitigating these impacts. And with that, I would like to stop it here and leave it to questions from audience if there are any. And recognizing my colleagues at UC Merced as well.
Thank you very much. It was amazing body of work